technical level now. So I'd like to introduce Mark Smith, a personal friend of mine, but also someone whose skills, knowledge, and abilities I hugely admire and have done for a long time. So Mark is a software developer with experience in a range of industries. He has been through many different organizations and brought his magic to all of them. He's known in the industry for teaching and helping people with awkward problems. And when he's not coding, he says you'll probably find him with a soldering iron building a keyboard. So I'd like to introduce Mark Smith. Thank you.
Hi, everybody, and thank you. That's probably the most praise I've ever actually had from Guy. And yes, I have some weird hobbies. Thank you for coming. I'm planning to spend the next 40 to 45 minutes talking about how some of the features of MongoDB can aid your compliance efforts. But first, just a little bit about me. My name, as mentioned already, is Mark Smith, and I'm a developer advocate at MongoDB. And the intricacies of advocacy are kind of irrelevant here, but it's worth mentioning that my experience is primarily in software development, and these days talking about software development to other software developers. So this topic today is a little bit outside of my comfort zone, so please forgive me if I get a little bit too technical or use slightly incorrect terminology around governance and compliance. I wanted to provide a tour of some of the features of MongoDB that I think are specifically applicable to your industry. I may hit or miss a few times, but even if it's not useful, hopefully you should find it interesting. So MongoDB was founded in fact, no, let's skip that because I've got that in a later slide. So to start with, this is just the sort of high-level topics that I'm going to run through. I'm going to start with the fundamentals of MongoDB, how it runs kind of physically, and what the data it stores looks like. And then I'm going to talk about how the architecture of MongoDB allows for high availability deployments with relatively little effort compared to other systems. Then I'm going to talk about where you store your data geographically and some of the features we provide to help you manage that. And then the main body of the talk really is the section on data security, where I'm going to talk about the many features that MongoDB provides around data security. And then I'm going to cover a couple of slightly miscellaneous features that we have around data management. There should be plenty of time at the end for questions. So let's start with the introduction. MongoDB is a newish one of a newish breed of databases that are really defined by what they're not. They're not relational databases like the ones that you may be used to. This sector is generally called NoSQL, but that's not really a very helpful term because most of these NoSQL databases really, they don't share very much in common. So in fact, they range from highly specialized databases that simply provide search functionality to build search engines or store time series data for monitoring metrics across your systems, and to much more generalized databases that can be essentially a drop-in replacement for a relational database. MongoDB is a general purpose database. It's mostly transactional, although it's increasingly providing support for analytics workloads on the data that you also store in a transactional system. It does, despite what you may read online, support transactions, and it has done for some time. It also supports joins if you really want to join across data. But I'll show you how some of the features of the data that you can store in MongoDB avoid the necessity of doing these locking operations on your data, which can really help with your scalability with write-heavy workloads. MongoDB also, for what it's worth, supports some of these more specialized workloads, like storing time series data efficiently and building search engines on the data that you're storing in MongoDB. So I mentioned MongoDB is a database server. If I didn't, then I'm skipping some of my notes. And you may think of a very simplified, like the most simplified deployment that you would want to push out into production like this, but you really don't run MongoDB like this. It's built from the ground up to be run in a cluster of at least 3 servers. The way that it works is your applications will always talk to a single node in the cluster. Well, in general purpose applications, you'll talk to this machine called the primary. The primary is actually elected by the other machines in the cluster. So when you put these servers together, you say, join this cluster, and then they'll have a little chat, and one of them will be elected the primary. And then your applications will connect to that. That machine is responsible for handling all the queries that you're making on your data. It handles making the updates and saving them to disk. And it also handles streaming the data to the other machines in the cluster that are called secondaries. So let's talk briefly about what we actually store in this cluster of servers. So this is the thing that really defines MongoDB, is that it's a document database. So we store these structured documents in the database. We store collections of documents. In fact, a collection is like a bucket of these data structures. So if you've worked with JSON data before or any kind of dictionary, this may look kind of familiar. This is actually my favorite document. It's from a sample movies database that we host for teaching people about MongoDB. It describes a movie from 1893 called The Blacksmith Scene, where this blacksmith hammers on an anvil, takes a break for a beer, and then goes back to work. It's 1 minute long, and it's basically a TikTok video from 130 years ago, so I thought it was kind of cool. So anyway, this document describes that movie, and there's a couple of things I want to highlight that really differentiate what a document is versus a row in a table. So actually, before I get to that, firstly, there's some types here you don't get in JSON. So I mentioned JSON, and if you've worked with that data structure at all, it's basically a sort of fundamental data type for sending data around the internet. But MongoDB doesn't actually store JSON, although you may find documents that say that it does. And that can be highlighted by the fact this ID type is not supported by JSON. It's a fundamental MongoDB type for storing primary keys. And then we've got this released value, which is in here. This is a Python representation of it, but it's a native date timestamp type, which is very useful in a database, as you might imagine. This format is actually called BSON behind the scenes, but you will never see BSON data because it's a binary format that can't be read by humans. So the other thing to highlight, that is a sort of differentiator from MongoDB and relational databases, is that you can store values that are non-scalar. So the value of caste and countries here are both arrays. Caste has 2 values in it. Countries has 1 value, and it's a single string in an array. It's worth mentioning that because it only has 1 value, I could have just stored that as a string, and other documents might, if they have more than 1 country, might store that as an array of strings. That's generally a bad idea. So the thing I'm trying to get across here is your documents within a single collection can have a different structure if you want to. But generally, where you can keep the same data types in your documents, you should, because otherwise in your programs, you need to account for every type of value that may be stored in that collection. The other thing I wanted to highlight, as well as arrays, we can also store objects as values. So this is embedded data that references IMDb data that relates to this movie. You would reference this subset of data through the IMDb key. So for example, if I wanted to access that rating value, it would be accessed as imdb.rating, and that would give you the value 6.2. You can also combine these 2 features, so you can store an array of objects. So you can really provide this sort of nested data where related data is stored together, so you don't have to join across data in different places. This is all stored together in one place on disk, and it can be updated atomically, so it keeps your data consistent. So that really helps with actually scalability and speed. The fact that often you can store your data together, you're not having to go look for it in different places. Queries. A database is not really a database if you can't query your data. MongoDB has a full Turing-complete query language, which is very powerful. I'm not going to get into that today because I don't think anybody here is particularly interested in it. Here is a sample query that looks up all the documents in a collection where the year is greater than or equal to 2000 or less than or equal to 2009. And I expect when I put that up, that was pretty incomprehensible. And then when I started reading it to you, it sort of made a little bit more sense. It can get quite complex. You can combine different parts of the query with different Boolean logic. You can conduct complex aggregations. Once you get started reading it, it becomes easier. So this query language is built from the ground up to allow querying of complex and nested data. And it's worth pointing out here that the query itself is a document, much like the things that you're storing in a database. A document is kind of a fundamental atom for MongoDB, the way that you work with it. It's also part of the network protocol that you use for talking to the server. But I mean, that's a behind the scenes detail. So just to sum up kind of what I whizzed through, MongoDB is a clustered database by default. It was designed that way from the very beginning. It's not a feature that was tacked on later, and that provides some big advantages, which I'm about to get into. It stores documents in collections rather than rows in tables, if you've worked with relational databases before. You can run it self-hosted, so it's actually an open source database that you can run on your laptop if you're developing stuff, all the way up to a fully hosted service, which I'll cover in just a moment. It's a general purpose database, so you can run a whole bunch of different transactional workloads on it, but it also happens to support some specialized data types, such as time series data. You can build a search engine with the Atlas search feature, and we support analytics nodes for running offline analytics that won't badly impact your production workload. So now to move on to the high availability thing, let's go back to the cluster diagram. But with this, let's talk about it within this context of high availability. So running these 3 servers does not give you extra performance. You can connect, if you want to, you can force a connection to a secondary to run analytics queries on slightly stale data. But it doesn't give you better performance overall when you're talking to the primary, because that's essentially a bottleneck in your cluster. The reason you run a cluster with more than one node is so that if something happens to one of these nodes, the cluster can continue running. So if the primary goes offline, or there's some network condition that means that the servers can't talk to each other anymore, the remaining servers, as long as 2 of those servers can still talk to each other, they will have a conversation with each other, decide that the primary has gone away, and they'll have a little election between themselves, which elect a new primary. And at that point, all the apps that are connected to the cluster will be reconnected to the new primary, and the server can continue as if nothing had happened. And hopefully behind the scenes, somebody is working on getting that 3rd node back up, because at this point, you're no longer running in a high availability state. If one of these nodes goes down, you don't have a cluster anymore, and the service goes offline. So this is also a feature for upgrading your cluster. So even if you're not running it, even if you're not worried about hardware failure, and you should be, you can take nodes out of the cluster on purpose, upgrade them to a newer version of MongoDB, and then put them in the cluster, at which point you take another node out of the cluster, upgrade that one, and put that back into the cluster. And so you can have 0 downtime upgrades. It's all automated through our cluster management software as well. So essentially, it's something you can do with a single click. So if you want high availability in the cloud, we're really talking about high availability. You want to put each node in a different data center or availability zone. So here I've just labeled these as coming from different AWS availability zones. And this is more than enough in most applications. It's worth noting that there will be latency between these nodes now, because by default, MongoDB, when you save data when you ask the primary to save data, it will stream to at least one of those secondaries. And only once a majority of the nodes have taken the data and journaled it to disk so that it can't be lost if the machine restarts, at that point, you will get an acknowledgement that the data is saved. So you would have to have a catastrophic failure across multiple data centers to actually lose data when you're running under this majority write concern. You can, if you want better performance, reduce it to 1, in which case the primary node will say, yes, I've got the data, and you can carry on. But if something then happens to the primary and the data hasn't yet been streamed to a secondary, there's a chance you may lose a few seconds of data. So this is a trade-off that you can make depending on your use cases. So for full availability, you want to host each node on a different cloud provider. And again, this is entirely supported. This is actually supported by our hosted offering automatically. You can select an option and then click checkboxes for the different cloud providers that you want to host MongoDB nodes in. For almost every use case, this is overkill, but there are an increasing number of companies that really care about resiliency to this degree. It also gives you the advantage of having the data in each of the clouds and taking advantage of the different offerings those clouds have. So for example, Google has world-class AI and analytics offerings. And so if you want to operate with your MongoDB data within Google Cloud, but also take advantage of various AWS services, you can have your data in both those places automatically. So that's a quick whiz through high availability. You want at least 3 nodes. If you want to take one of those nodes out of the cluster or have one of those fail and still be high availability, you can have 5 nodes or 7. This provides 0 downtime upgrades. If you really want high availability, you should run these nodes in different data centers. You can run them in different cloud providers through MongoDB Atlas if you want to. And you should think about right concern when you're configuring your cluster to get the trade-off that you need with regards to risk versus performance in terms of data resiliency. So the next thing I wanted to talk about was a pretty advanced feature of MongoDB, a feature called sharding, which often comes up in conversations about MongoDB with reference to scaling. So you can run multiple clusters in parallel. So those clusters that I mentioned before are called replica sets because each server has a full replica of your data set. If that gets too large to store on a single machine, so we're really talking petabytes of data now, you can divide the data by some criteria, and then you store one subset of it on one cluster and another subset on another cluster. And then you can run this service called Mongos, which I think is short for Mongo Shard, which pretends to be a MongoDB database. But in fact, it works out for each query, it works out which clusters it needs to send that query to. And then it takes the results from those clusters and merges them together and then sends them back to the client. So this really allows you to scale almost linearly with huge data sets. But I don't want to talk about it in that context here because I don't think that's super interesting to you. I want to talk about a different use. Oh, in fact, there's an example here where you're storing lots of books and you can divide them up by color if you want, or you could divide them up by the first letter of their title, but then you don't get such a pretty version of the diagram. It's probably better to shard by users because then when you're doing a query for a specific user's data, you only need to run it on one shard, which is just better for scaling generally. So you'll be making lots of requests for lots of users, and that then divides up, hopefully evenly across the different clusters that you're hosting. But when you start talking about users have a location. And so you can pin different users to different shards. They're actually hosted physically in different locations. So here, to reduce latency, you would store all of the European users' data actually in Europe somewhere. And this has interesting implications for compliance because there are certain countries that obviously have restrictions about where the data can be stored. Europe is a good example with GDPR and not without permission exporting data, for example, to the Americas. A conversation I have with many German developers is, can we keep the data within Germany? So you could specifically create a shard, host it within a German data center, and then all of your users' data will be migrated automatically to that data center. And every time from that point on, every time that you save German users' data, that will automatically be stored in that shard. So you have options about keeping data local to a specific area. Another feature that was actually launched last week, we just had our big annual conference in New York, so I'm quite jet lagged at the moment. We've launched this feature called Cluster Sync, which can also solve a handful of compliance issues. So our replica sets have always included synchronization between the nodes in a cluster, but it's now possible to have a whole other cluster kept in sync with your primary cluster, potentially in another location. So this provides lots of flexibility with regards to where you host your data. You can either host it in 2 or more locations simultaneously, and then if there's a massive event in, say, the cloud where you're hosting your data, you can fall back to an on-premise installation. Or it's a backup plan if you need to migrate your data off the cloud. And I know various regulations require you to have a backup plan for moving away from cloud provision. So currently, this only works with MongoDB 6.0, which is in it's a release candidate at the moment. I believe it's scheduled for a release in a month's time. So this isn't actually quite available. It's available to play with, but not available to put into production yet, I would recommend. Oh, and I didn't have a summary slide for this section. That's throwing me off a little bit. Let's talk about data security. So we have the standard features that you would expect around authentication and authorization. We use Scram for password authentication. This is essentially a handshake that happens between the server and the client. That means that the client doesn't ever have to send the password to the server. We support X509 certificate authentication if you want it yes, anyway, let's not go into the details of that. We also support AWS IAM integration if your organization is using that. We support LDAP integration, and we support Kerberos. None of these are very interesting, so I'm not actually going to cover them in any detail. I just wanted to highlight that we do support all these standards. We also support role-based access control. As you might expect, that's pretty much a standard in the industry. With regards to network security, that is also kind of boring. So if you're hosting on Atlas, our hosted offering, we support restriction by IP address. We also support VPC peering, so that you can tunnel into our VPC for accessing your servers. And we support TLS encryption over the wire by default. We support VPCs and this tunneling supported by AWS and Azure Private Link. This is on MongoDB Atlas. So again, not hugely interesting, but we do support various ways of accessing your data over the wire without people listening in. I think more interesting and a more unique feature to MongoDB is our storage engine supports encryption at rest. So if anybody was to get hold of one of your hard disks that's not running the software, they would hopefully be unable to read the data. So you would store your key in a key management service. All the major cloud providers have them, or there's HashiCorp Vault. And then it means that once the database is shut down, that data is not readable it's encrypted as bytes. Another feature we have around ensuring that only the right people can access the data that they're supposed to see is a redact feature in our query language. And the way this works is, as part of your query, you provide this redact block. All our operators start with $, which is why it's called $redact. And as your document is passed through this stage, think of it as a pipeline that documents pass through when you're querying them, that either filter them out or modify them. In this case, it would remove the sections that aren't supposed to be seen by that user. And the query type is quite dynamic. You can add business logic to it to basically say that if this user is not supposed to see green, then remove the green functionality. It doesn't have to be related to the user. You can say, if it's currently Wednesday, remove everything that's not pink. I'm sure there's only one person that got that joke. So this is really meant to be used in an architecture where you build some trusted middleware that will be responsible for data redaction. So in this case, your application is authenticating with the middleware in some way, telling it what user it represents, and then the middleware is modifying the queries to ensure that the data that is supposed to be redacted is redacted. And it only has to provide that as an operator in the query, and the database will actually do all the work to make sure that recursively any data that user isn't supposed to see isn't seen by the user. So that's just removing the data at the query level. I think a unique feature that we have is a feature called client-side field level encryption. And this is similar in the sense that it ensures that users are not meant to see the data that they're not supposed to see, but it really applies to in the situation where you've got a privileged user who gets access to the database when they're not supposed to. The way that this works is you specify the fields that are privileged in the database that you want to be encrypted. You integrate with a key management service, and then you use that MongoDB will automatically encrypt that data before it's sent to the server. So before it's even sent over the wire. So the key is provided to the driver within your application, but it's never provided to the database. So even if you were hosting it on MongoDB, where we have root privileges, we still wouldn't be able to understand the data that you're sending to the server. So there are two methods of encryption. One is called deterministic. this would be used for storing something like a social security number in the US, which is considered privileged information, and you don't want somebody who gets a dump of your data to be able to match up social security numbers with other user data. But you may also want to be able to search by the social security number. That's essentially an identifier for a user. So in this case, it's encrypted in a deterministic way. So this value 1, 2, 3, 4, 5, 6 will always be encrypted, in this case, as A, B, C, D, E, F. And that means when you want to then query the database, all you have to do is, in fact, this is done behind the scenes by the MongoDB driver. It will just automatically encrypt this value when it's doing the lookup. It comes to the same value, and then it can do essentially a plain text search of the database to find the matching values. So this is extremely powerful, being able to store encrypted data and still query on it without having to worry about this. This is just done at the schema level. You just say, this should be encrypted, and it will be from then on. But for social security numbers, that's not a problem because they're unique. They're not related to other people's social security numbers. But let's talk about something like, say, a medical test result, where you've got a bunch of documents in your database storing the test result, and those have all been encrypted as values. But you can see that the first, John and Rita both have the same value. So even without being able to decrypt that, we can tell something about these test results. And it's even worse if we can find out what John's test result was by some sort of social engineering thing. We phone him up and find out what his test result was, because now we know what Rita's test result is as well, and anybody else who has the same value in the database, because we're using deterministic encryption. So this is not ideal for this kind of information where the same value may appear in different places in your database. In that case, you want to use what we call randomized encryption. So in this case, now when we encrypt 1, 2, 3, 4, 5, 6, we may get A, B, C, D, E, F the first time, but the next time we encrypt it, we're going to get a different value. And this means we can't query on it anymore because you can't determine what the value is in advance. It's always going to be different each time you run the encryption. So now you have the ability to encrypt data automatically for certain fields in your database, but you can no longer query on it, which is a limitation. So what I've just described to you is called client-side field level encryption, and it's version 1. So we actually released version 2 last week, and it's going to be an interesting thing to describe. So it's called queryable encryption. So this has the benefits of both of those types of encryption. It is randomized, so it has non-deterministic values. So you never know what this value is going to be on the right-hand side each time that you encrypt the value on the left-hand side. But it still remains queryable. You can do exact match querying on it. The key is never sent to the server. The data is never decrypted. It's pretty efficient. And it's cutting-edge, peer-reviewed open encryption. But I don't have any idea how it works. So if it seems like magic, then you have the same opinion that I do. The research papers are being published, I think, in about a week and a half. So this, at the moment, only does exact match searching. So we have the same capabilities as the first version of CSFLE. But this encryption methodology also will allow us to develop searching for values in a range or searching for strings with certain prefixes or suffixes. And we'll be adding some of those operations in upcoming versions of MongoDB. Yeah, magic, no idea. So the auditing, we have an auditing facility in MongoDB as well. So if you just want to monitor what is happening in your database, we have that built in. So the auditing facility will write auditing events to the console, the syslog, a JSON file, or a BSON file, BSON being the native binary format that MongoDB uses internally. It can record things like schema changes. So if somebody is adding or removing collections of documents, or if they're modifying the configuration of those things, if they're modifying your network topology, so they're changing your replica sets or your sharded clusters. It can also log authorization and authentication. And if you want to, you can turn on logging of all create, read, update, and delete requests, but that will have a significant performance impact on your server. I think, so more specific to MongoDB, I want to talk about a feature called change streams. This is a feature that your developers would implement, and it allows you to monitor a cluster or a database or a collection for all updates. So every time an update is pushed into your application or your database, sorry, all of those updates are sent as events to the software that you would develop for your specific requirements. It doesn't record read operations, so it's not useful for monitoring things like authentication or whether somebody's accessing records that they shouldn't. But if you want to keep track of how data is changing and who's changing it, potentially you could build an application to monitor data provenance, which I think could be quite powerful. And finally, I would like to talk, again, like at a relatively low level, kind of developer level, there are some real opportunities for middleware here. So software that sits between your application and your database. So as you're sending queries through to the database, you can intercept them and parse them. So as I mentioned before very briefly, these queries are data structures. So because MongoDB doesn't use SQL, which is a language that has to be parsed and is relatively complex, because it uses these data structures, you can write relatively simple software to understand what the query is doing and flag things that maybe it's not meant to do. And that would, or even block it. So you could report or block queries at this stage before they ever reach the server, which I just think is an interesting opportunity that just comes from this feature of MongoDB, the fact that it uses data structures as queries. So that covers the security and privacy section. We have authentication, role-based authorization. We have encryption on the wire. We have the ability to redact data based on dynamic properties. We have field-level encryption, which is now magic. We have auditing, which allows you to monitor events in your database. We have change streams that allow you to track changes to your data over time. And potentially you could build interesting middleware to monitor and guard against unacceptable uses of your unacceptable queries reaching your database. So now, just the final section, I just wanted to cover a couple of Atlas-only features that I thought would be interesting. So these are, again, as I say, they're from MongoDB Atlas, which is our fully hosted offering, where we will host MongoDB on AWS for you, or Azure, or Google Cloud, or a combination of all three, if you like. So these aren't available in the software that you'd run on premises. So first, backups. There are various ways to make snapshots and store them online. That isn't an Atlas-only feature. That's available in all versions of MongoDB. I'm assuming you all understand why MongoDB's redundancy is not enough for data resiliency. But if you don't, I just want you to imagine one of your DBAs running delete database on your cluster, either by accident or on purpose. So you need offline snapshots. We have the ability in Atlas, or there's a thing called MongoDB Cloud. I've totally forgotten what that feature is called. That's not good. There's a sort of halfway house where MongoDB will monitor and manage your cluster for you. That cluster can consist of nodes on laptops or in production services, and you get a nice console that will just tell you how things are running, allow you to do upgrades, things like that. Atlas and that cloud service will allow you to run on demand or just recurring updates. It sits on the change stream feature that I mentioned before. So it's monitoring all the changes to your database, and it's just spooling them to disk. And then every so often you take a snapshot to say this is the state at this time. Especially in sharded clusters, that's essentially the only reliable way to take a snapshot of your database. So you really, if you're running a significant operation, you're going to want one of those two options. Cloud Manager, I have it in my notes. I knew I had it somewhere. MongoDB Cloud Manager or MongoDB Atlas. And then finally, Data Federation, which is an Atlas-only feature. As your data gets larger, you need a strategy to remove data from your database, just to allow it to continue to perform acceptably. But better than deleting data is obviously if you can archive that data to some kind of cold storage. So MongoDB Atlas contains this feature to automatically archive data, matching certain criteria to S3 buckets. So it just stores it as efficient binary files within S3. The reason I think this is interesting is because it remains queryable. So although you take it out of your production database, as it were, your sort of hot database, you have the ability to query just your live data within the MongoDB cluster or your archive data in S3. It's not hugely efficient because you no longer have indexes that allow you to do efficient lookups. But if you're doing data analytics on the vast amount of data that you've stored over time, it's relatively sensible to do a document scan. On top of that, you can also do a query across both data sets if you want to query both the live data and the sort of cold storage data. So this really allows you to persist data indefinitely while also potentially keeping the size of your hot data manageable. So this is all the stuff that I covered today, which is quite a bit. I hope it wasn't too much. I'm not going to just read through it because essentially I've done that already. I hope that you found this useful or at least interesting. Thank you. So I think we have some time for questions. 2 questions.
Hello.
Hi.
Thank you for that. That's been really interesting. I'm mainly only really worked with relational databases, so it's quite useful to see kind of what NoSQL and Mongo databases can do. This may be a bit of an unfair question, but I think maybe about sort of 5 years ago, around that time, I think MongoDB potentially had a bit of a reputation for insecure deployments. So specifically kind of Internet of Things devices where the vendors hadn't set up the database properly and let it all open to anyone who wanted to. I'm just wondering, why specifically on MongoDB? What sort of went wrong there, and what's it sort of doing now to help users sort of do better implementations?
I'm actually really glad you asked that question. I go around the world giving this talk called "Everything You Know About MongoDB is Wrong." I cover that. So this is a mistake that the company made. A mistake. It was a decision the company made, was to make developers' lives as easy as possible from day one. There were some data resiliency issues around this as well. So the write concern that I mentioned before, that is now majority by default, which is robust, used to be 1, which means that only the primary will have received data. And that meant that sometimes people lost data when their cluster collapsed. With the very first release of MongoDB, the write concern was 0, which meant that the data hadn't even been understood by the server. You could send an update to the server and it would just go, yep, sure. And you were meant to check later that the data had been persisted. It was, again, it was a decision. It was a bad decision. The default, we've changed the defaults over time for data resiliency. We've done the same with security. So the early versions of MongoDB, they had no authentication configured by default. You were meant to set up configuration before you ever exposed a database to the internet. And that just meant that lots of less experienced developers spun up MongoDB on their server. They then wrote an application against it that ran on the same server. They never thought about installing a firewall, and then they essentially spun up the same configuration on the internet. Sometimes it was a little bit more complicated. Maybe they scaled up and they moved their application off the database server onto a second server, and then they couldn't get to it anymore because there was a firewall on the database, and so they just switched it off, at which point all their data became exposed, and somebody goes in and just deletes all of it for fun. These days, they go into an unauthenticated database, encrypt all your documents one by one, and then add an extra document telling you where to send Bitcoin. Maybe not now. I think Bitcoin's crashed. I'm not sure that's worth anything anymore. So we worked with the Linux providers to change the default configuration with their distributions of MongoDB. We still have a problem with that, to be honest, because the license of MongoDB changed. A lot of the default distributions of MongoDB are very old and not secure, not particularly performant. They are kind of 7 or 8 year old software. And the whole database has been rewritten since then. But if you download MongoDB and from our website, it's freely available, and install that, then it will be secure by default. You actually have to provide a really scary looking flag if you want to expose it to the internet or any network without having authentication installed. And it keeps on warning you every time you connect to it that you need to set up authentication. So I kind of answered two questions. One you didn't ask, but I thought I would cover that anyway, just in case you were wondering about that.
Thank you.
Hi, regarding GDPR.
Could you hold the microphone a bit closer? 'Cause I aren't-
Hi.
Hi.
Regarding GDPRs, if you go back to the shards, you said you can have data locally in one shard. So
Yep.
we'll say we have data in Germany in that shard. And is it allowed to query data overseas? For an example, if we query data from US with keywords for the specific shard in Germany, then you will transfer data at the time of query.
Not sure I understand what you're asking. I think I understood the first part. And you talked about saving
So you
data
have the data in the shard for the Europe or the German. It's saved in Europe,
Yeah.
but you query data from the US.
You what data, sorry?
Query.
Query.
Yeah.
Yes, so
Then you transfer the data from.
yes, it would transfer it. It wouldn't store it. But then you're explicitly requesting data. But yeah, you're right. That data would then be transmitted to potentially a client in the US.
Thank you.
Hi, thanks for your talk. So in terms of the resiliency piece, what's the difference between what Mongo's doing versus what the cloud's doing? Because obviously the cloud provides a lot of resilience and provide backups across countries. And so are you using the cloud feature, or is this a separate Mongo feature? Sorry.
Both.
Okay.
So we have our own. Essentially, that architecture of the servers provides the resiliency that you get. It's clustered by default,
Sure.
but often it's run on cloud infrastructure, and so whatever infrastructure is provided by the cloud, sort of beneath MongoDB, will also be inherited.
Okay, yeah. So that's what I thought. I thought the cloud was doing it, so I just wasn't clear.
No. It's like primarily the feature there is MongoDB specific.
Okay, thanks.
Hi, thanks. A couple of questions. With the risk hat on, who actually owns MongoDB as a company? And secondary question is the monitoring stream, I think you call it change stream. Does that hook into any industry standard sort of monitoring tools?
So the first question, MongoDB Inc. owns MongoDB. So we're a public company. I can't remember what exchange we're listed on, but yeah, we're a public company. We're 15 years old. We host databases for banks, pharmaceutical companies, various other established sort of highly regulated industries. And the second question, change streams, not that I'm aware of. We have, if you're hosting on MongoDB Atlas, you get some analytics tools. There's a sort of charting and analytics product. It's not hugely in depth, to be honest. It's built on change streams. We link into Kafka. That's although it is built on change streams, we have a Kafka connector. So you can either use MongoDB as a source or a sink. So you use at either end of your Kafka workflow. And we also have a product called it's not quite related to the sort of streaming analytics, but if you want to conduct analytics on MongoDB data, we have a thing called the BI connector, and a brand new feature that was launched last week that I've actually forgotten the name of. It's like MongoDB SQL or something like that. It's quite ironic for a database that's called NoSQL. But we provide two SQL interfaces on top of MongoDB, specifically for the ability to take things like Tableau or Click and connect them to your database.
Hopefully this is a little bit more of a basic question. You know, when you had the clusters and you have the primary and the secondaries, and you have them across different data centers and different data center providers, surely you've got latency between them. So how I mean, would some of the secondaries not think, oh, wait a minute, I'm on my own now.
and then try to fail across, and then you got the application not knowing which one am I speaking to? Am I speaking to the primary, which secondary now? Sounds like it's all fall into a bit of a mess.
Yeah, that's not a simple question at all. That's a really complex question. That's essentially the problem that we solved with building a clustered database. So you're absolutely right. And it's not just across data centers. There are weird network conditions happening inside, say, AWS all the time. Any sufficiently large network will have these problems. You get things called network partitions, where sometimes server 1 will be able to speak to server 2, but server 2 won't be able to speak to server 1. And some of the most complex bugs we've had in earlier versions of MongoDB have been related to these weird network conditions. Every time we've ever had one of those reported, we've resolved the problem in sort of a patch release in a very short amount of time. Currently, we're not aware of any issues around that. But the cluster is designed to be self-healing in those kind of situations. You don't, if the cluster kind of comes apart and then comes together later, because there's always a majority of machines in the cluster need to be able to talk to each other to keep the cluster up. That means you've always got a source of truth. It's always those machines that were the majority at the time. And so once the sort of rogue node comes back in, they can then get it back up to date again and essentially self-heal the cluster. We use a protocol called Raft. It's modified Raft, if you want to really get into the weeds, which is it's a standard protocol for actually doing that kind of cluster management. Okay, I think I stunned them to silence.
Thank you very much, Mark. That was mind-bending. So we're going to take a break for lunch now, so that will be served upstairs. We'll be getting back in here for about 1:15. But before we break, I feel it's worth taking a moment just to mention the general support we've had for our event today from Sapphire, who have, well, they'll tell you themselves upstairs about the services they offer, and they do have a very wide selection of freebies if you want to take advantage of that. But we're very grateful for them giving their support today, for coming along, and for providing our next speaker, who I will touch on after lunch. We do have one small request. They are obviously keen to be able to catch up with anyone after the session. If you do not consent to being contacted by Sapphire, if you could just check in at the registration list at the front and make sure there's a very visible, obvious X next to your name, so that you are opting out and having been reminded about GDPR just there. But otherwise, go enjoy lunch. Thank you very much.